The next talk is by Professor Zhao from Beijing, Superconductivity above liquid nitrogen temperatures in barium yttrium copper oxides.
First of all, I would like to thank Professor Ashraf, Maple, and Chu invited us to be here and give a talk about our work. The title is Superconductivity above liquid nitrogen temperature in barium, strontium, lanthanum, yttrium, copper oxide systems. So this work is done in joint groups at the Institute of Physics, Academia Technica. So at the beginning, how to start work, I give the brief introduction. When I read the paper is written by Battlog and Mullers, I find out the idea of the Mullers' idea was reasonable, because at that time I thought, so the inerrant electrons between the copper 3 valence and the copper 2 valence, so the moved in between them is they are in the neighbor. So this makes the case the alternative John-Taylor effect. This makes the neighbor cells the distortion and to give the vibration. This case the strong interaction could lead to the high TC. So this idea I told my friends, and with the Professor Chen, he is also is here and start to work in China. In December of 1986, in our experiments, we find out in the strontium, and the lanthanum carbon oxide, I find out critical temperature at 48.6 K, and with TC of 10 K. And for the barium lanthanum carbon oxide, so the onset of critical temperature 46.3, and with TC of 7 K. So I show you this. The pictures. So you may worry about why you didn't do experiments lower than the 40K, because that time my colleagues are just interested in the 70K, so they don't want to do more work about it. But later on, several days later, the sample exposed to air is so change the change of the critical temperature. And this one is for the barium lanthanum carbon oxide. This is the point at 40.6.3. And here we did the measurement on the thermal power. So these the two curves is the original samples as I showed just above. So you can see that this point is the thermal power decrease dramatically at about 40 Upright magnetic fields up to 7 Tesla. Just a little bit deviation from this point. But from this thermal power measurement, I think that the portable superconductivity a little bit may exist above the 40 50 or higher. The portable superconductivity at around 70 in some sample we have observed the reasons follows that. One is resistance decrease to 0 dramatically around 70 So, but this phase unstable and couldn't be reproduced in the next test. So I like I mentioned above the sample with the TC of the 48.6 is a little bit stable, but this one is very unstable. And the thermal power I have shown you, and the AC magnetic susceptibility only showed some traces. So for this reason, I believe that the high TC phase around 70 exists in the metastable phase. For obtaining and stabilize the metastable phase, the three methods should be adopted. One is quench, second, the high pressure, and third, impurity doping. for the pushing the TC to 70K, the quench and high pressure ineffective. So I have to do some experiments to use the quench and high pressure. We haven't got the sample with the high TC. But the only way is left is to doping impurity. At the beginning, we make the samples use the materials is not so pure, because some of them is the chemical impurity, but sometimes good. For example, for the rare earth lithium is chemical impurity. So using we use the spectrum pure materials of the TC of the barium and strontium and lanthanum carbon oxide. Only the critical temperature only appear around 40K. So meanwhile, the X-ray powder and electron diffraction analysis show that the crystal structure of the potassium 2 nickel phosphorus 4 with the 3 period of the superconducting superstructure. This is corresponding to the superconducting phase at about 40K. So because these materials, we know that is the layer perovskite structure, but for this reason, we suggest that keeping the framework of the structure with barium and lithium and use some of the elements with a smaller covariance radii instead of some of the barium and lithium. A system more close to the two-dimensional and with a longer period of superstructure could be obtained. As mentioned above, the Mueller's formula is not good to obtain the single phase, but it is good for getting the new metastable phase, which could have high TC. For this reason, we make the new samples. Use the yttrium or other elements instead of the lithium or barium. We use the same formula as we did before. The first sample with the TC of the 93K. They were found in the barium 0.5, yttrium 4.5, copper 5, O5, and plus 3 minus Y. This means it's easier to get high TC metastable phase, even though not so much, but easy to find this formula. The result taken from earlier sample as follows. You see that this is the AC magnetic susceptibility is the onset of diamagnetism is at 93, but for the resistivity transition is we saw that the midpoint is 92.8, but onset we suggest that above the 100K. Even so, the resistivity deviation from linear at 110. But zero resistivity with resolution 2 multiplied 10 to minus 8 voltage determined is 78.5K. This result is we use the pickup system to do the magnetization, and to confirm the result we obtained use the AC magnetic susceptibility. The onset TC is near here is about 93. This magnetization orders magnetic fields. So with the different temperature, we can see that for the 90K, it still can find the diamagnetism near these very low fields. We how to determine the onset of the TC. So we use the different current to measure the resistivity transition. We can see that the different current at the onset, just the derivation from the other curve is at 110. So, but I have to point that. So this phenomena is not only from the superconducting transition. here we would like to show the several samples we made with different composition and different heat treatment. So the AC magnetic susceptibility measurement shows the nearly same critical temperature, but for the resistivity, it's much different. So you can see that how to determine which point is the onset of the superconducting transition according to the resistivity chain. Here we apply magnetic fields. So it's up to 70.2 Tesla. So we can't find the obviously difference at above the 100K. So this is the one that joined the line is not so good, but should be a little bit different about less than 100K. Just before I left, a good sample have been obtained. So at the beginning, with the ratio of the superconducting phase to the whole volume is just about 10%. If the samples without multiply connection region, but before I left, we got new samples. Is critical. The superconducting ratio of superconducting phase is more than above 50K. So I show the results like this. Here's the results. This the onset of transition is very sharp. It's like a resistivity transition. So the point is 94. And here is the resistivity transition. The zero resistivity near 90. The measurement, because the measurements on the Hall effect, specific heat, acoustic attenuation, infrared absorption, and the way preliminary results show the whole conductive characteristics. I suggest that the composition of the multi-phase could be adopted for the searching for the high TC phase. Then optimize the composition. We have made thin film of the strontium lithium carbon oxide. I think that for the application, the device should appear first. Thank you very much.
Thank you. Next talk is bulk superconductivity in single-phase oxides at temperatures above 90 Kelvin by Bertram Battlog.
Okay, thank you.
That should be all right. Okay, thank you. Good evening. I would like to talk about, give a short summary of an extensive work that has been done on oxide superconductors at Bell Labs over the last few years. And these are the people I would very much like to appreciate their collaboration with. And I would like to mention two names in particular. Excuse me. It's Bob Carver and Bruce Van Dover. Superconductivity research in oxide superconductors that goes back quite a few years. As Professor Miller has pointed out, we have been working on Thank you. We started working on barium lead bismuth oxide quite 5-6 years ago, and through our work on very high quality single crystals, we gained lots of insight about these oxide superconductors. Then through the last 3 months, through substitution of strontium in the lanthanum barium copper oxide, TC was raised to 38 degrees. And finally, I would like to concentrate on the latest compound because it has the highest TC, and also because we don't have much time to talk about the other ones. I will not present many experimental curves, but rather like to emphasize how similar all these superconductors are among themselves and how much different they are from the rest of the superconducting families. After we heard about the superconducting behavior at around 95 degrees in the copper yttrium barium system by the Alabama-Houston collaboration, we realized that it was absolutely necessary to identify the superconducting phase in order to gain further insight as well as to possibly proceed to higher TCs. Therefore, we started a systematic investigation of the ternary phase diagram, starting with a few known compounds and this composition that was published. Less than 3.5 days after we got this report from Houston, we had identified the superconducting phase as being barium-2, yttrium, copper-3, and some oxygen there. Oxygen was not known. As you can deduce from some rules, this is the green compound which lies down here. So if one makes, which is barium, yttrium-2, copper-05, as we just heard also before, if one makes this composition, we automatically get mainly, say, 2/3 of the green stuff and 1/3 approximately of the superconducting material. Through detailed oxygen analysis, we figured out that the oxygen concentration should be 0.7. So we can talk about essentially an oxygen-deficient perovskite, which generally would be written in AbO3 times 3. However, we don't have 9 oxygens there, we rather have 7 oxygens. At that time, we proposed an orthorhombic cell a long time ago, 2 weeks ago actually. And in the meantime, a single crystal X-ray diffraction work by Sigris and Sunshine have confirmed this original projection. And that's a structure of, that's one unit cell. It appears rather dark. I apologize for that. I would like to point out that we start out from the perovskite, stack 3 layers of them. But since we do not have 9 but 7 oxygen, we have to take out 1 complete layer adjacent to the yttrium and 1/2 of the layer around here. So what we are left over with essentially 2 layers of copper oxygen, which are slightly buckled. And then in this layer, a random distribution of oxygen vacancies amounting to 1/2. That's the structure starting from this insight and observing that the barium and the yttrium are regularly distributed. That's why we get 3 unit cells there. We have 3 times the A site occupied here. We started immediately substituting at different sites, and that's just a preliminary list of compounds we made. Don't focus on all of them. I just like to point out that one can substitute both on the barium side as well as on the yttrium side. And one particular nice substitution, which I like, is the one with europium. Completed substitution with europium. It drives up TC quite a few degrees, gives a very sharp transition, which is less than 1 degree wide, actually 0.7 degree wide, from 90 to 10% level. I will come back to this particular compound later if I talk about upper critical fields. So instead of showing all the various U graphs, I just flash this one resistance curve. On this resistance, I would like to point out one thing particular. It is that the resistivity, it is a normal state behavior, which is quite unusual. First of all, it is a quite good material if you would extrapolate down there. It's a damn good metal. Not only, of course, it goes superconducting there with a quite narrow transition width in itself, but also this linearity in resistivity has not only been observed in this material, but also in the lanthanum-strontium copper oxide and in the barium-lead bismuth oxide-based single crystals. We never published that, but we have them. So there's a commonality in these oxide superconductors. This linearity and resistivity, together with the very unusual optical properties that Jornstein, Gordon Thomas, and Doug Rapkin measured in our lab, I don't have time to show them, and also the fact that in the normal state, this material has a considerable Curie-Weiss contribution to the sustainability. All these 3 facts together make us believe that these are not ordinary metals at all. And these are taken as ingredients to some theories, and we'll have a talk later tonight which invoke unconventional pairing, meaning non-electron phonon pairing, leading to superconductivity. That's one aspect. Of course, these are measurements on phase-pure material. And there's absolutely no second phase whatsoever there, undetectable in X-rays. One acid test for bulk superconductivity is a true Meissner effect, not to be confused with DC magnetization or AC sustainability measurements. In an experiment like that, one cools the sample steadily in a field without moving the field, nor changing the sample position with respect to the field. What you observe is a very rapid drop at TC, and there's a Meissner signal of about 76% of independently measured diamagnetic value. This is a very large value compared to any superconductor because one always has trapped flux in a sample. So that's a lower conservative limit of the bulk of the volume fraction that is superconducting, and I think it's the best measurement to prove that it is bulk superconductivity. Let me summarize all the data on this view graph. Don't read all the numbers, that's not necessary. But I like to compare the three compounds here, barium bismuth oxide, lanthanum strontium, and the barium yttrium copper here with each other. These are TCs. Of course, we measured HC1 magnetically, HC2 as functional in resistive measurement up to very high fields at the magnet lab. We measured up to 30 Tesla resistively. These are the values here, typically about 1 to 2 Tesla per degree, a slope for the upper critical field. Now, there are 2 points which I like to point out. One is the Sommerfeld parameter, which we have derived from various measurements independently. They all give consistent results, and I was somewhat surprised seeing the large value of 25. We found for the barium yttrium copper oxide a gamma value in the usual units of millijoules per mole Kelvin squared of about 3 to 5 only, which is even lower than the one in lanthanum strontium and is only slightly higher than it is in barium lead bismuth oxide. So these are very low density of states at the Fermi level compared to others. I will come back to this point explicitly in the next view graph. Then there is the next point which we would like to keep in mind. It's not only measuring HC2 for potential applications, but rather we would like to know what the critical current density is. Well, great. We have here in barium lead bismuth oxide, the critical current density, even in very good material, was only about 10 amps per square centimeter. Westinghouse Group, I think, will report tonight other measurements. We agree with them having values of order 1,000 amps per square centimeter. And when we did the measurement on the barium yttrium copper oxide at 77 degrees and 0 field, just dunking it in helium without a sophisticated measurement, we could not drive it normally because of our contacting problem. We can say that the critical current density exceeds 1,100 amps per square centimeter. That's a very nice number for a beginning. Let's come back to superconducting materials here, and I'd like to compare this oxide superconductors with all the rest of superconductors we know. I hope you find your favorite down here. If not, we can put it on. It will certainly not exceed this line. That's an empirical line beyond which no superconductor had been observed. It's a TC versus gamma plot, a double logarithmic scale, so we can catch the recent developments here. So if you flip over our oxide superconductors, that's where they are. These are the red points, barium lead bismuth oxide, lanthanum strontium copper oxide, and the 90-degree material. It is rather clear that their TC is about a factor of 4, in this case it's higher than the TCs of comparable superconductors, and in this case the TC is a factor of 10 higher than it is for superconductors with a comparable density of states at the Fermi level. I take this as a quite interesting indication that one might have to think about new mechanisms for superconductivity. And I'm sure that that's a very active field going to be over the next few years. In the meantime, however, let me assure you that development in terms of potential technical application have already started. And if we want to do that, one aspect is looking at the upper critical field. And that's a collection of the upper critical fields, again, for the 3 favorite oxide superconductors. And that's the blue line. Just concentrate on the higher one, highest TC material here. That's the blue line just for the barium, yttrium, copper oxide. We substituted part of the yttrium by europium and found an upper critical field slope, which is about roughly 3 times higher, taken at the midpoint. You can imagine where it extrapolates to. It goes something like, 2 megagauss or so, if you extrapolate it down t equals 0. That's not the point to make here. I think we should be somewhat conservative and say where does the material go normal, and that's indicated by the width of the bars, because the transition broadens in high fields due to the fact that one has anisotropic behavior. Okay. The anisotropy of the conduction state, very much like in the layer compound, smears the TC out. So if we were to make a magnet out of that, just in our minds, and like to operate it at 77 degrees, we would be able to operate it in a a field range, say, for 20 Tesla or so, to be somewhat conservative. That is the same field as we get under best circumstances nowadays in our labs, and we are very proud to have these magnets that work up to 18 Tesla at 4.2 degrees. That's one aspect which I find fascinating. Do we have wires of that? No, we do not have wires, however. I can show you something else which I find quite interesting, and that brings up a point which we haven't stressed this evening yet, namely that these compounds are ceramics. These compounds can be fabricated in all the highly developed ceramic processes. For instance, what comes to my mind is making a superconducting toroid, as for instance this one, that's superconducting above 90 degrees. It traps flux, as Mike Georgi has measured. The toroid was made by Dave Johnson. That's not a superconducting solenoid yet, but I like to show you something similar to that. Namely, it was surprising to me that those things exist. One can make tape of this material. That's in the so-called green stage, where the material is not fired yet. That's one piece of that here, as you might see. You can shape it in any form you like. You can wind it up for a coil or whatever you like, then fire it, and you have a superconductor, which we have measured, and I just got the curve here. This foil indeed goes superconducting above 90 degrees. Okay, so let me finish with the following remarks. Barium lead bismuth oxide was the beginning. We recognized it. Many people did not recognize it, that this was a highly underpriced stock in the market of high-T superconductivity. Lanthanum-strontium oxide was the next step. Now we did all the work I just described to you, and there are many reasons why we are excited in working in this field. One is the physical aspects of it. We are having low gamma materials, very high TCs, and we certainly have to think about new mechanisms, at least think about them. That's one way I think we are all glad working in this field. The other thing is that, as I just tried to convey a little bit of a flavor of it, it might be quite possible that to the fact that these are ceramics, that we have high upper critical fields and not so discouraging values for the critical current density, which might lead us to potential applications a few years from now, and I think our life has changed. Thanks a lot.
Thank you very much, Bertram. We now have 20 minutes for a discussion in which you can ask the panelists questions. Can we turn on the lights? Is that okay? Just so I can see someone when they raise their hands. Okay, any questions that you want to ask the panelists? Yes.
I'm Robert Hazen from the Geophysical Laboratory, and I wanted to comment on the structure work. There have been a couple speakers that have noted in their structure work copper and octahedral coordination. We've done single crystal structure work on these and have located the oxygen positions with some precision, and we note no octahedral copper at all. Most of the coppers are in square planar coordination. A few coppers are in 5 coordination, but this gives the structure a unique feature, that is sheets of copper oxygen which are not linked to each other. So each sheet of coppers in the structure is isolated from each other, at least in terms of oxygen coordination. That's all.
Thank you. Any other questions or remarks? Anyone else? Yes. See, can you come to the microphone, please? Give your name and institution.
Mein Name ist Batra Harmuller. Haben Sie eine Idee für Zimmer-Temperature Superconductor machen?
Can you repeat that in English?
Not a particular one. Maybe Dr. Chu wants to answer this question.
That's what we call to pass the buck away. I think there is a strong indication, as I mentioned, that For example, if we look in history, back in November when we saw something drop in the lanthanum copper oxide, barium copper oxide, 70 degrees. And then it was not reproducible at that time. But then now it's stabilized, it's 90 degrees. So now if we use extrapolation of that kind of history, then I believe room temperature is possible because right now there are lots of indications of superconductivity, indication of superconductivity as high as 240, as I mentioned, observed by our laboratories and also by a Berkeley group.
Yes. Can you use the microphone, please? If you can, I think there's one in back of you there.
My name is Gabor Forgács. I'm from Clarkson University. I think in the first talk, Dr. Müller showed curves where actually the resistivity went first up and then it dropped down. And he actually used the word localization. The system wanted to become localized. And then in the last curve, last talk, we saw curves just the opposite. There was a steady decline, and then the system went superconducting. Now, is there really any reason to assume that there is the system has anything to do with localization? You are showing samples with thesis of the order of 40 Kelvin. Well, it's hard to believe that the system has anything to do with localization, but maybe it does. Could you comment on that?
First about our early curves, these were barium substituted one. The barium ionic radius is quite larger than the lanthanum. If instead of barium you substitute with strontium, which has practically the same ionic radius, you don't see this upcurving. It comes linearly down, as has been shown in some other curves. Now, if you don't dope it, then it localizes. But this has nothing to do with the superconducting features. There you apparently have a fuzzy band where the Fermi energy lies.
Any other questions?
More questions.
Yes.
The question is about the tape. What is the transport property of the tape that was shown which is flexible, and what is the last step to that to make it superconducting?
This tape I showed you, which I just folded away, is in the so-called green stage. That's what Ceramis told me. That's the state before it's being fired. So you make it in any shape you like and fire it appropriately. And then what you end up with is a product, which I also have here a box of, is a thin material that looks like that. If I can hold it steady enough, it's a thin foil which is fired and has all the typical ceramic properties. About the transport properties, all I can show you was the resistivity that I showed you before. We don't know yet the critical current densities, but I think it's just early in the stage that we have not improved things or they have not optimized them at all.
I believe there's an arm back there somewhere.
Are comments possible or just questions?
Questions are preferable.
Okay, this is a question before the previous one. Someone mentioned the word localization. I think if you are near the half-filled band, I remember my thesis of 17 years ago, where there are great difficulties in convergence in looking at a tenfold degenerate Hubbard model between antiferro and ferro. You're going to have large frustration. In addition, you're going to have the two-dimensionality, which by the Merman-Wagner theorem will prevent not only any ferro or antiferro magnetism, but it'll preclude and quench any possible magnetic fluctuations. So you're in a place where nothing possible can interfere with a possible superconducting state.
Okay, thank you. Okay, Marvin Cohen has a short remark to make. Marvin?
There have been some inaccurate descriptions of the Berkeley research in this area, and I thank the organizers for allowing me to make a brief statement which supposedly should clarify what was done. Like many of you, we began working on the lanthanum compounds when we heard of the pioneering work from the IBM Switzerland, Zurich, and when we heard about the Houston, Alabama discovery of a 90-degree unidentified superconductor, we began knowing only this, to try the yttrium barium compounds and independently discovered superconductivity in yttrium barium copper oxide. We submitted a paper for publication, and when Paul Chu announced his material on March 2nd in Berkeley, he graciously acknowledged our independent findings. A reporter from the San Francisco Chronicle attending Chu's lecture wrote a reasonably accurate account of our duplication of Chu's research, including the duplication of the observations of unusual drops in the resistivity for temperatures as high as 234 Kelvin. Although the Chronicle article stated that the scientists stressed that these samples were not superconducting, an overzealous copy editor thought 234 Kelvin was a better number than 100 Kelvin. And in contrast to the body of the printed article, erroneously stated in the lead paragraph that we had discovered a 240-degree superconductor. A prominently displayed correction acknowledging the editorial error was printed the following day in the Chronicle. Unfortunately, even prominently displayed corrections are not terribly newsworthy, and the true events may not have been transmitted accurately to all of you. Hopefully this won't happen in the future when we have superconducting transmission lines.
Thank you, Marvin. Let's see. Any other questions? Yes.
There was substitution for several rare earths in the system. Said that came from the transition temperature. Do you have evidence that they have unusual magnetic properties as well as superconductivity?
See, can you give your name and institution?
Bob Markowitz from Northeastern University.
Thank you. Anyone want to answer that?
I can comment on that. We know that TC is only very marginally affected by the substitution with rare earths. In particular, the case I've shown you was the europium compound, which increased TC actually by a few degrees and sharpened the transition. We don't have very detailed magnetic measurements. All I know is from my own measurement is that it has a very substantial Meissner effect. In addition to that, the normal state susceptibility in the europium case is clearly indicative of the trivalent europium state dominated by the Van Vleck singlet triplet excitation, J equals 0, J equals 1, splitting of a few hundred degrees typically observed for trivalent europium.
Yes, Paul?
Yeah, well, when we look at that, I think basically the TC is not very much affected. And whether it really enhances the TC or not, I'm not sure, because it's almost independent from our results. And our transitions are very sharp. And as I mentioned, the AC diamagnetic shift is almost 97 to 100%. And I think I just forgot to mention earlier that I think right now, if we talk about interfaces in this kind of compound, I don't believe they exist between different phases. If it exists within one phase due to the unusual structure, that possibility still cannot be ruled out at this moment. And as far as magnetic properties is concerned, even yttrium, just like Battlog just mentioned, we also observe antiferromagnetic Curie-Weiss behavior with a negative Curie temperature, and indicating there is a strong antiferromagnetic interaction in that kind of material.
Okay, any other questions?
Back here?
Okay, where
Yes.
are we? Okay, yes. Please give your name and institution. As Professor Krumhansel pointed out, this is important to do because of PhysRev V as in video, because this is all being recorded.
Okay,
Go ahead.
Jim Wynn, IBM Research, Yorktown. Can someone say something about the mechanical properties of these materials? Maybe the speaker from Bell Labs can say what happens to the ductility or malleability of the thing after it gets fired?
I think the mechanical properties are best described as the ones of a ceramic. And if you drop a saucer, you know what happens. If you take this baked tape, it is quite fragile. It can be bent, but it is fragile. If you're interested about microscopic measurement of sound velocities, compressibility, and things on, we can discuss it later on. We did those things. But the question is, can we make a wire out of that? I'm not a specialist in the field. But considering that the compound is known for 2 weeks now, essentially, I think it would be somewhat premature to make any conclusions about that.
Dr. Mueller.
Well, you should recall that if you use tapes, the tapes contain all chromium oxide and iron oxides, and they are very reliable. So I see no reason whatsoever that one can, in the future, not make tapes. And of course, in these compounds, it may be better to use the these metallic oxides on some thin copper foils because of the reliability in carrying current. It should further be pointed out, if you talk to people who make these large magnets, that it is not necessary that the resistance of the whole wire is zero. If the resistance is already of the order of a 20th of copper, then the engineers are already happy. So in this respect, one can be optimistic in case one can have sufficient high critical currents.
Yes, Paul, you wanted to make a remark?
I believe it's just like Dr. Miller said. I think the wire, just we have to have cladding with copper, with the material embedded in the copper, because that will, for safety reason, in case the material goes to normal, so we won't burn the whole thing up. And I think the process probably will be developed later.
Okay, there was a question back there. Yes.
I would like to know, since there's lots of talk about other mechanisms, if it's not a secret, if there are any results on the substitution of oxygen 18 for oxygen 16. Since phonons are a possibility, I guess that would be a way of looking at things. Are there any results for oxygen 18 replacing oxygen 16?
Anyone want to respond?
Yes. Phil, if you come tomorrow in my lab, I have your results for that. At the very moment we are doing oxygen exchange, we did the first oxygen 16-18 exchange a few weeks ago on the 40-degree material, but it was a very small fraction that was exchanged. I was guessing it only a few percent, so that's not very reliable. A few days from now, we have the result. It's baking actually at the very moment in the autumn.
Yes, Dr. Miller.
I think the question you ask is a very important one to decide between the various theories which have been proposed.
Yes, Paul?
I believe that's going to be a very difficult experiment also. Of course, with Bell Lab, I'm quite sure they'll get good results. And the reason is by making the sample, the reproducibility and the width of the transition, of course, Bell Lab has done a tremendous job by reducing the transition. But then the second thing is the transition width, and then the second thing is how reproducible the transition temperature can be made. Until that, the isotope effects experiment can be rather difficult.
I think there was one way back there.
Yes, this is Alan Goldman from the University of Minnesota. I was wondering whether one of the panelists might comment on related compounds that might have, for which they might not have succeeded in producing superconductivity. The failures.
I think that has something. If you ask our families, they can tell you how many nights we have spent away. And if it was just measuring the few view graphs that we present and publish, we would have been able to do it in a few days. I think our notebooks are filled with compounds and derivatives thereof, of which did not work.
Dr. Mueller.
As I said, we tried 2.5 years before we found the first layer compound. And so I can just agree with what Dr. Battlog said, and perhaps the specific one which we tried first was the perovskite, which contains nickel 3+, which is metallic, and then we replaced gradually the nickel 3+, say, by aluminum 3+ to reduce the bandwidth in order to get the interaction, what we thought of the Jahn-Teller stabilization of the order of the bandwidth, and this only localized, probably because you have random fields inside.
Paul?
I think it's a good question. In fact, there are more failures than success, basically. And in fact, for each element, at least we found that way. I don't know how Belt or other groups found. For each different kind of a compound system, they have different sample treatment conditions. Appearing they change from one to the other. So if you want to look for this, try to be careful and don't give up easily.
Dr. Mabel, can I make a comment from University of Tokyo about this? My name is Dr. Kitazawa, and I'd like to speak for Professor Tanaka. And in our university, at around the beginning of December, we have got many green stuffs out of various lanthanide barium copper oxide system. So I told the student, don't get green ones. They would not become metals. But actually, what happened was the temperature was too high. And we were firing at that time at 1100 degrees centigrade. So all stuffs became green. And later, we found that when we fire at lower temperatures, all becomes black and all becomes superconductive. So around 900 degrees centigrade.
Thank you. Bertram, yes.
Thank you very much. May I just make one additional comment to that? When I was describing our work on systematically investigating internal phase diagram, it turned out that it was not enough just to wear the composition. We had to wear all the heat treatment procedures and the oxygen treatment procedures. So it is an n-dimensional space you have to work in the lab. So it is not just the composition at all. It's incredible how things change above and below 1,000 degrees, for instance, or whatever the magical number is. So it's lots of work.
Okay. Yes, Paul.
I think Dr. Battlog is perfectly correct because apparently we found that all the sample preparation conditions, including reaction time, reaction temperature, quenching rate, and compositions, are all interrelated. If you change one, the rest will change. So you really have to do it very carefully and patiently.
See, one more quick question right from you, please. Yes. Go ahead.
What is the natural abundance of lead and other these exotic materials? And do you envision that this will be a serious limitation to kind of large-scale applications that everybody's expecting now?
Okay. What is the natural abundance of lanthanum and other elements that these materials are made of? And do you foresee this to be a serious limitation on how these will be applied in the future, or something like that? Anyone?
Are you trading the stock option market? Despite the fact that they are called rare earths, they are not so rare at all. They are quite abundant, and they are not very expensive. They are only expensive if one wants to buy them in high purity. It is quite foreseeable that the yttrium stock is very small at the moment. If you want to order anything from a supplier, you have to wait for a long time. But that should not be a major problem in future time.
Okay, I'd like to thank the panelists. Very enjoyable presentations and discussion. Thank you very much.